Yeah. So let us start. We should wait for some more time. What is your suggestion? Students,
Sir, maybe we can start. They'll join.
that is better idea. Okay, so last time we were discussing about infiltration, right? You supply water or apply water to the field. It first reaches to the ground and it is starting infiltration. So infiltration is entry of water into the soil. So last part of this learning is about infiltration. It is remain, that is empirical method. So measurement of infiltration you have learned. Do you recall that? In theory part, not in the lab. We learned that there are two methods, single cylinder or single ring infiltrometer and double ring infiltrometer. So up to this you have finished. Next is empirical methods or empirical equations which are used to estimate the infiltration. Remember, it's in estimation. Estimate the infiltration. Now, let me have pointer because I missed my pointer today. So there are four methods or four equations to estimate infiltration empirically. All these four equations are empirical equations. Empirical means, anybody? What is the meaning of empirical?
From observations or experience.
Observations, number of observations, and we are developing a relationship. So these are based on observations, and these observations have been done in different types of soils, varying from sand to clay. So all possible soils they have incorporated to develop these equations, empirical equations. Let me go one by one. We have this first is, if you recall, it's first is Kostyakov equation. So Kostyakov developed this relationship in infiltration and time. Water is poured or water is stagnated on the surface of soil in 1932. So Kostyakov developed an equation basically describing infiltration of water into soil. And what is the relation he has developed? This is simply infiltration rate in centimeter per hour is equal to K, that is property of soil, since it's a compactness, it's a loose or whatever condition it is, and T to the power minus N. And define the type of soil. K is property of soil and N is basically the type of soil. Which type of soil? So K and N are constants and T is the elapsed time basically in minutes. So time in minute, K and N relates to infiltration, rate of infiltration. I is infiltration rate in centimeter per hour in this way. So if we want to find out what is the accumulated total water, depth of water in the soil, because that is our purpose. We are simply interested how much depth of total water got entered into the soil in this particular time. Is not that if we have applied water in the field, it is our simply idea to know how much water got infiltrated into the soil or entered into the soil. So if we integrate this equation with respect to T, it gives another expression which describes the accumulated depth of water or accumulated infiltration in the soil in time T. So if you are integrating this with respect to T, you can see it will be K divided by 1 minus N or N minus N plus 1 and T to the power minus N plus 1. So this is the basic equation first developed by Kostyakov in 1932 to find out the soil characteristics in terms of infiltration rate and to find out accumulated infiltration in the soil. However, it has limitation. If you just see this equation, it has a limitation. What is the limitation? Suppose we are increasing time to quite long, say towards infinity. It's longer time. So once it's longer time, the value of I, our infiltration rate, will go towards zero or negligible, zero. However, what is the practical condition? Anybody? Can you imagine what could be the practical condition? Because you have also means completed or done this lab, at least observations you have seen. So what is your guess? Anybody? Students, are you there?
Yes, sir.
So what is your idea? Infiltration rate with time. If we increase time towards a quite long time towards infinity, what will be the real practical condition of infiltration rate?
Sir, you're asking how maybe one day.
Maybe 10 days, not 1 day, maybe 10 days, suppose. So if we are continuously flooding soil with the same depth of water, say for 10 days, what will be the infiltration rate after 10th day?
Sir, it will be
It will be
constant.
it will be a constant value. It will not be zero. Yes or no? That is
Yes, sir.
what I want to know or want to let you realize it that infiltration rate will not be zero, but it will be a constant value, right? So in this way, this particular equation has a kind of limitation. When time is infinite or very long period, Postikov equation indicates that infiltration rate will approach to zero after this long period of time. That is not correct because it's a constant value entering water into the soil. It will not be zero. And in this way, it has a kind of limitation. However, it represents infiltration adequately, means it gives quite correct information about infiltration rate and accumulated infiltration in the soil over a limited period of time, means just like 1 day or even 2 days, which is generally satisfactory in irrigation practices. But this is not correct. Suppose we are interested to sorry, find out the amount of water infiltrated into the soil, say from a pond of water, right? So there it will not be correct condition. So this is basically limitation of Kostyko equation. However, it works well for irrigation purposes and we can use this. Next empirical relationship was developed by Lewis and Milne, and this is also known as Horton equation. You might have heard most about this equation because this is mostly used in soil and water conservation or basically in hydrology. So it's also known as Horton equation. This is also an empirical equation like Kostyko equation, and it has a relation. Lewis and Milne developed relationship of cumulative infiltration or accumulated infiltration with time, and they have given cumulative infiltration y that is equal to a constant t plus v into 1 minus relationship is exponential minus rt, and here a, b and r are constants. So we need to find out from the observations data to set up these parameters or to set up this equation and find out the value of these constants for a particular condition. Once we have from Lewis and Milne accumulated infiltration, we are as well interested to find out what is the rate of entry of water, that is infiltration rate. So if we simply differentiate this equation with respect to time, we can get the information about infiltration rate. So dy by dt, if we are doing, then it will be simply, the new relationship will become I, that is infiltration rate, A plus Vr e to the power minus RT. You know it better. So this is how we are getting from these standard equations both the conditions, accumulated infiltration as well as infiltration rate. Why it was developed? Because after getting information about Lewis and Milne equation, it has a limitation of estimating infiltration rate quite negligible or zero after quite long period of time. Lewis and Milne developed this equation to overcome that condition, and it does not give zero final infiltration rate like Kostyakov equation. So this has a kind of improvement over Kostyakov equations, Lewis and Milne equations. Now next equation which we can use to find out infiltration rate as well as accumulated infiltration is Phillips equation, which was developed in 1957. So Phillips derived the equation for vertical infiltration. Vertical means downward, vertical only. It is means infiltration means it may be entry from lateral as well, but it was especially a known condition was developed for vertical entry of water from the surface. And they also related cumulative infiltration or total amount of infiltered water in the soil with respect to time. So here in Phillips equation, cumulative infiltration was related with sorbivity of the soil, S, that is the soil property, T to the power 1 by 2 or zero point 0.5 plus AT, where A is parameter that depends on soil properties again, and T is the time. So in Phillips 1957, it has used a soil property by measurement. In previous equations, they have not used any measured soil property, but Phillips first time used measured soil property that is called sorbivity or sorptivity. So soil property that is called sorbivity is the function of initial and surface water content of soil and water diffusivity in the soil. Diffusivity means its movement in the soil. So that is already a property of soil. So to find out infiltration rate from this cumulative infiltration relationship developed by Philip, we again differentiated this y, that is cumulative infiltration with respect to time, and we can find out means by changing this relationship towards this. So this is the way how Philip related infiltration rate and accumulated infiltration with soil properties. Here, sorptivity is used. Now, the last relationship, let us a little bit know about soil sorptivity. It is basically defined as sorptivity y is cumulated infiltration with respect to time, and relationship is t to the power half. Basically, it sorptivity measures the capacity of the medium or soil to absorb or dissolve, means accumulate or remove liquid by capillary action. So simple idea here Phillips has used that soil is not a medium, but it's basically transmitting water in different phases. Suppose it's a dry soil and you are applying water, it is not a kind of push flow. Push means once it is saturated, if you are adding single drop of water at the top, at the bottom you can get one drop only. But it's a movement in terms of capillary. The moment water reaches, it is not saturated. So water moves through pores and in capillary action as well. Through pores means under the flow of gravity or means force of gravity as well as capillary action. And that's why they have used sorptivity. So it can be determined, this sorptivity, from horizontal infiltration when water flow is mostly controlled by capillary absorption, capillary condition. And if infiltration observations are available, the value of sorptivity and A, that is A is again the parameter that depends on soil properties, means it is again soil characteristics. So we can find out the value of sorptivity and A characteristics, A parameter that is representing the soil characteristic. So in this way, three questions, Kostico, Milne, Lewis and Milne, and Phillips. And then the last empirical relationship was developed not by a researcher, single researcher, but it was a kind of department where such kind of activities were performed as a project. And that is, you know, because you have already learned USSCS curve number that was developed by the same department. So now it is USSCS Soil Conservation Service Department, which means who also developed, means that department also developed infiltration relationship with respect to soil characteristics or observations. By using the observations, they have developed an infiltration relationship with the soil properties. So it was developed again in 1957, and in their relationship, they have connected accumulated or cumulative infiltration with the time and two or three parameters A, alpha, and V. So these are constants representing the soil properties, soil characteristics, and varying A, alpha, and V from 0 to 1. So to find out infiltration rate from this empirical relationship, cumulative infiltration is again differentiated with respect to T, and it is estimated as infiltration rate relationship A alpha T to the power alpha minus 1. That is the simple idea. So there are four equations developed to estimate infiltration rate and accumulated infiltration in the soil, provided we know the soil properties that is represented by constants. So in SCS, it is A alpha B. In previous, it is soil sorptivity and A, two parameters. Further in Lewis and Milne, it is A, B, and R. And in Kostico equation, it is K and N that is representing the soil property, along with the sorptivity that is measured in Phillips equation. Now, once you have idea about, remember, if you are asked to measure the infiltration rate or infiltration characteristics of this of a particular soil, you have to go for experiments, and there are two only methods basically: single cylinder or single cylinder infiltrometer and double cylinder infiltrometer. But if we have observed data for the soil properties in terms of infiltration, we can set up four equations or four models. These are to find out continuously the infiltration characteristics or infiltration property of the soil with respect to a certain condition. Now, to make you clear, especially I have taken one example of Phillips equation because you have observations for our field or farm. You can fit these equations to those observations. I have given you for 100, I think 50 minutes, 1.5 hours, sorry, 3 hours, 180 minutes. So you can fit these equations. But this is just example to let you understand better how these equations are used or fitted for a particular soil condition, so that we know the parametric value for rest of the calculations later on. So this is just one example. While conducting the double ring infiltrometer test at a site, the following observations were recorded. Using these information, developed developed the Phillips two-term model for this side. Phillips equation, this is sorptivity based, in which basically cumulative infiltration is recorded. We are observing. And sorptivity and A characteristics means parameter that depends on soil properties A, we used to know. If we know these two properties of soil, we can fit the equation to any condition with respect to time. So this is the basic idea of getting value of sorptivity and a parameter representing the soil characteristic from this information. Can you write down this? Students, can you do that?
Yes, sir. Yes.
Okay. How many are 35? Okay, no problem.
Sir, you want us to find the answer or you want us to take down the question?
This means I will submit these slides to you, but the idea is how to do that. If you are not doing here, you will only see the slides because I have solution as well. So can you do by your own? I have very short condition. As you want to see this, let me show you. It is here, and the third part is here. Here ends the equation, learning. So can you do a little bit by your own? I am showing you the solution. So you also need to do at the same time so that it is practice, a kind of practice to your learning.
Yes, sir. We will do that.
I think it is correct, or you feel it is absurd idea? What do you feel? Should we
It is
do
okay.
or should we means pass on, ignore it at present?
No, sir, let us solve it.
What do you think we should do? We should do?
Yes, sir,
Okay.
yes.
So these are the observations, time versus cumulative infiltration. And write down the equation. I don't have my pen today. I cannot write. It's a completely dark down. How many of you are here in the campus? Almost everybody, or you are attending classes from home?
Some
Yes,
of
sir.
us are
Most are in campus.
Eh? I couldn't get you.
Sir, most of us are in campus.
Campus. And it's a lockdown. That's why we are also not allowed to go to the department. I couldn't bring my writing pen here. Note it down, the data. Note down the data, everybody, please. To say something to let me know.
Sir, two more minutes.
Okay, 2 minutes. Is it over? Finished it?
Yes, sir, I finished.
Okay. Now, write down this Kostyakov equation first. Phillips equation, sorry. Because we are fitting Phillips equation. Cumulative infiltration y is equal to S t to the power 0.5 plus A t. And I, that is infiltration rate, that is in, what is the unit of infiltration rate? In all these relations, we have taken centimeter per hour. That is 0.5 st to the power minus 0.5 plus A. And t is taken in minutes. So if you have these two equations, can you fit or can you calculate the infiltration rate of this observation? Can you do that?
Yes, sir. Yes, sir. We will give a try.
Okay. Infiltration rate. And infiltration rate is estimated in centimeter per hour. Anybody calculated infiltration rate?
Sir, one more minute.
Let me know when you finish. calculation of infiltration rate from this data. Okay, how to calculate?
Sir, using Excel, like fit the model.
Infiltration rate from cumulative. Fit the model to find out the infiltration rate. What it is given? It's a given lapse time
Y is given and
and
T is given.
that is T. Elapsed time means total cumulative time. Just like the last information is for 140 minutes and total infiltered water in centimeter is 14.94 centimeters. So now suppose here I want to know what is the infiltration rate, how to find out that? For last characteristic here, the last observation. What is infiltration rate here? Anybody? I need an answer so that I am getting connected with you. It's basically thinking. You think about the problem, you will get answer immediately. You are just looking from me that I will tell everything. Certainly, I will tell everything, but that will not be useful much for learning. So, what will be the infiltration rate at the last? Let me get this information from you. What will be the infiltration rate for this data at 140-minute time? I can show you that I have. But what about your learning? Anybody? How to get that? It's not the number I am looking for. I am only interested to know whether you guess it correctly. How to get that?
Sir,
Sir,
using the table, we have to find S and A uh, by
Taking?
fitting the curve. We have to find S and
No,
A, like
no, no, no,
plotting.
no. No. That is fine. You have seen the graph, it is used at the last. But my question is not that. My question is to find out the infiltration rate at the time 140 minute.
Yes, sir, that's what. Like first find S and A and then insert the value T equals 140 in dy by dt equation and then
No,
get
no,
the
no, no.
sir,
Listen.
14.94 minus 14.02 by 10.
Yeah, that is the right way. Because this is the cumulative infiltration and it is time. So if you are dividing cumulative infiltration by time, it is the average rate of infiltration by this time. That is the simple I wanted to know. And that's why this is the purpose of asking you to solve this. Otherwise, example is solved. I prepared for you to let you learn or to let you understand. That is okay. But if you are not thinking, you will not get the right information to judge the problem. So here you can see, let me show you now the answer for this particular example. You have time, elapsed time, and you have y, that is cumulative infiltration. You can match, it is 0.86, 1.12 here. This is cumulative infiltration, that is called y. And we are interested to find out infiltration rate. Here we have time, we have cumulative infiltration, and here it is infiltration rate that has been calculated. So it started from 0 time to 3 minutes, that is just 3 minutes, and this is the amount in centimeter that infiltered. So in 3 minutes, it infiltrated 0.86 centimeters. So simple idea to find out infiltration rate is what will be the condition in 60 minutes. So it is coming like this. Then the second observation at 5 minutes. So it is changed from 3 minutes to 5 minutes. That is the difference in time is 2 minutes, and accumulated infiltration difference in these 2 minutes is the difference of 1.12 and 0.86. So that amount is in 2 minutes here. What will be the condition in 60 minutes? That is the infiltration rate. And at the last, in the same way, from 130 minute to 140 minute, that is 10-minute difference, infiltration or accumulated infiltration of water is the difference of these two observations, 14.94 minus 14.02, and this is in 10 minutes this difference. So we need to find out what will be condition in 1 hour 60 minutes, and that is infiltration rate. So this is so simple idea to find out infiltration rate from the equation, from the observation. It is a simple idea. Now we are fitting all the parameters, are trying to get parameters to fit this same idea when we do not have observations. And this Phillips equation, if you recall, it is relationship with absorptivity and time, root T. Let me show you once again here. Cumulative infiltration is Y, that is related with absorptivity, and T with power 0.5 and A and T. So infiltration rate I is related simply 0.5 S T to the power minus 0.5 or 1 by root T. This is T to the power minus 0.5 means what? 1 by root of T plus A. So there are two conditions only, infiltration rate versus 1 by root T. 0.5 S and A are there. So this particular relation is used to find out the value of S and A in this equation. So what we are doing, we are trying to get, or we have calculated 1 by root T. We have time here, right? And then we are using this information to plot the graph between infiltration rate, that is in centimeter per hour you have estimated here, and root means 1 by root T. So relationship between these two is giving you simple idea. Sorry, here I put F, but it is infiltration rate. I have taken from different source, so it was F there. I need to change this. F is equal to I. So infiltration rate in centimeter per hour is related to this equation what we have derived, that is 0.5 st to the power minus 0.5 plus A. That is the usual relationship, infiltration rate versus 1 by root T. So once we are fitting this data, infiltration rate you have estimated here, and you have 1 by root T, and once you are fitting these two information into a curve and trying to get a relationship, it will give you infiltration rate that is given here by F is equal to, relationship is simple, that is linear, 0.5 st to the power minus 0.5 plus A. And this equation fitting its relationship, this relationship, it is simply given y is equal to mx plus c by least square method, that is usual. And here it is in Excel, you can put this data and find out immediately what is the linear relationship. So that we have achieved 17.35x plus 3.7. And this is exactly the relationship. Y is equal to mx. M is the slope of the data. X is the x-axis value, whatever we have taken. And C is the intercept here. to y-axis. So A is simply the intercept of this relationship. How much? From this equation we can see 3.7011. So A is equal to 3.7011. That is the parameter for this Phillips equation in this particular soil condition. And the second means 0.5 as t to the power minus zero point 0.5 is exactly 17.35 x. So what is x here? That is simply t. So 0.5 s is equal to 17.35. T to the power point minus zero point 0.5 is exactly what we have taken in x-axis. So this is x. So x is related to are exactly same 1 by root t. So here 1 by root t is t to the power minus zero point 0.5, which we can relate with x. So remain 17.35 is exactly 0.5 s. S is sorptivity. And now you can find out what is the sorptivity of this 12. That is 34.70. And now you can put the infiltration exactly equation that is given by Phillips. Infiltration rate I or F is equal to S2 to the power minus zero point 0.5 plus A. That is the simple idea. In this way, we can find out what is the value of sorptivity and what is the characteristics of the soil which has been taken in this particular relationship. So now sometimes it's important to think about
Excuse
how
me,
we
sir.
can find. Yeah, please.
Sir, in the equation we use time in minutes or in hours while calculating.
Uh, I'm not getting your question because it's a connectivity problem. Can you repeat it, please?
Sir, T is in hours or T is in minutes?
T is in minute always, always. Now, in this relationship, this is empirical relation. Infiltration is centimeter per hour and T is in minute usually in all these relations. It's okay now?
Yes, sir.
Okay. Any other question? Any
Sir,
question related to infiltration?
sir, I solved it using y is equal to st power zero point 0.5 plus 80, but I am getting
Okay.
different answers.
That's why it means we need to take care about the relationship. Means here data relationship. Can you share it to me? I will see how are you getting different. You have fitted the equation to cumulative infiltration rate, right? Sorry,
Yes, sir.
cumulative infiltration.
Yes, sir.
And you are trying to find out the value of
A and
S
S.
and A.
Yes.
Okay. My simple suggestion is, have you taken care about this power 0.5? Whether the fitted equation is in exactly form.
Yes, sir. Yes, sir. I did like that.
Then it should be quite near value to this because there are two conditions. This is simply fitting in linear relationship. Is not that? It's a linear relationship we are fitting here. Y
Yes,
is
sir.
equal to mx plus c is a linear relationship. So we are fitting simply infiltration rate and 1 by root t condition as a linear relation. But because you are using software, it is using different approach to fit a non-linear condition as well. Because it's you can see the observation, it is non-linear. Here at least 1, 2, and 3 observations are quite far away from this linear condition. That's why it may have a little deviation.
Sir,
Can you check
actually,
that?
yes, sir. Yes, sir. I will share it right now.
I will check this and will try to explain why. why it is not now. You just send me, and I will check later on because it's a class time, so I need to go to planned means objectives. Reason being we have to complete this as well. But certainly I will try to answer. So you just write down your name in the file and send me. Okay?
Okay, sir.
Okay. To my email. Okay. So do you have any query related to this? I hope you have learned infiltration. It can be measured by single cylinder and double cylinder filtrometers. And then second way is estimation if we have observation and soil properties relations or information about the soil constants or soil properties constants. So there are four methods: Kostyakov, Milne, Phillips, and USSCS 1957 method. So there are four methods. Is it clear now? And you have seen just one example how to fit the soil means fit the observations to find out the field characteristics used in these equations. And one lab certainly I have given you fit the data to find K and N and A alpha and B value in USSCS 1957 method. Is it okay? Any query, any question related to this? Otherwise, let us move to second process in the soil once we are applying water. Should we stop it here and move to another learning?
Yes, sir.
Anybody
No.
answer? Okay. There are 41 students, increasing now 40 students. Sorry, one. I am as well here. So this is infiltration. What we have learned. How what happened once water is applied to the field? The first learning to you is it infiltrates into the soil or it enters into the soil. That is called infiltration. What could be the next? Once water entered into the soil, what will be the next?
Percolation.
Eh? Yeah,
Water.
you are right. Percolation. Percolation. Basically, in one word, if you are to define, it will move inside the soil, right? In any way, any direction, it depends on the condition. So it's here. Now it is basically the dynamics of water. Dynamics inside. Inside dynamics, how it is affected. It's basically dynamics of water. You will see that once we are interested about irrigation, we are usually, or at the last I will summarize with these conditions, we are measuring soil moisture or soil water, right? How much amount of water it has improved or it has taken by the soil. That is one way. So it's basically a static condition. Water has entered into the pores and it is inside the soil, but it is not moving. But when we are applying, think about this, it is unsaturated or dry soil, we can say. Water enters into the soil, it is not saturated, so it moves because of gravitational force or because of gravity, as well as in pores, capillary action, because it is free space where air is stored or air is absorbed there, means occupying that void. So slowly air is released, removed, and water fills the voids. So in this condition, water is basically dynamic. It is moving from the top surface inside the soil, within soil, so it is moving. So here we can say it is basically dynamic are non-equilibrium condition. It is moving. So it is non-equilibrium condition exists when the soil water is subjected to movement. Basically, that is water movement inside soil. And flow of water in that sense may occur in two-phase system. Two-phase means solid and water. You have seen soil is three-phase system usually. Solid, water and air, or soil particles, soil, water and air. So it can move in two-phase or three-phase system. Once it is saturated completely, we assume that air is removed. So that is two-phase soil system, and three-phase once water is there means it is unsaturated condition. So in two-phase movement, it is voids are fully filled, means void volume is completely filled with water. So it's water and soil only. But if it is three-phase system, it is partially filled condition, means air is still there. Once it is continuing process, certainly all the air theoretically, practically is a different thing, but theoretically we assume that all the air is removed from the voids. So it becomes saturated, and it is now the saturated flow. A flow occurs when the voids are fully filled or completely filled with water. An unsaturated condition is if flow occurs when the voids are partially filled, just like infiltration. So in this sense, there are number of terms evolved, and we are usually taking into account while we are estimating the amount of water that we have applied for irrigation purpose and its movement. So one condition is water intake, the movement of water or irrigation water from the soil surface into and through soil. Means it is entered into the soil and then it is moving within the soil. And remember, we have discussed one time that it is a certain depth of water we are considering as a root zone depth where we have interest. Beyond that, it is soil, but it is not important for irrigation purpose for us. And once water passed the root zone, it is going to a unsaturated zone and finally getting to the groundwater either vertically down, or if laterally or horizontally it is moving, it will come up somewhere where it gets the depression, like in channels or rivers maybe, and so on. So all these paths of water movement as well as direction are termed differently. So movement of water for irrigation purpose from top surface soil into and through the soil, that is water intake. It is expression of several factors. Several factors means it's not only the entry, it is not only the vertical movement, it's a lateral movement, it's a depression somewhere. So it is basically the different topographic setting which includes number of conditions and gives us number of factors. So several factors including infiltration and percolation. So there are few terminology we need to make it very clear here. So I correct this. That is important. Why it is happening. And this is smaller, but it is okay. Sorry. Can you see the slide?
Yes, sir.
Can you see the slide? Okay. So it's a water application or basically precipitation. You have already learned in last semester, land and water resources engineering, what is percolation and what is seepage, to make this clear. So if it is precipitation, there is some interception you might have heard, and I'm sure you have learned it in hydrology. Some water is lost in interception and then it is reaching on the ground surface. So once it is on the ground surface, it's infiltration. Water enters into the soil. You can see from here. It is basically water enters into the soil here. Once it is entered into the soil, it is moving vertical, that is called percolation. Deep percolation means once it's passing a certain depth below the soil, that is beyond the root zone depth, it is deep percolation towards the groundwater. Or it is moving laterally. Later doesn't mean when I am telling that it is moving in this direction. It is not always in horizontal, perfect horizontal, but in any path, radial kind of flow, radial flow. So it is basically the seepage. It is laterally going, so laterally it may meet to the groundwater somewhere, it is topography, or it is coming up on the surface, say in depression condition like channels or rivers. So term percolation, basically it's a downward movement of water through saturated or partially saturated soil in response to force of gravity, or it's a gravitational flow of water under saturated or maybe sometimes unsaturated condition. Just like infiltration, once water entered into the soil, it is not governed directly with condition of soil exactly, because it's a dry soil, so water moves fast under the influence of gravity, as well as it's moving because of capillary action there. So there is percolation condition. Downward movement of water beyond the root zone to the water table, it's basically called the percolation, downward percolation or deep percolation once it's meeting to the groundwater. And then comes the second condition, it's a seepage. So lateral movement of subsurface water into the soil, that is seepage. There are a few more terms. It's basically the soil characteristics. We are interested about the soil characteristics behind all these movements. What is that? It's basically the permeability. What is permeability? You can understand this term very easily. It's allowing something to pass through. So property of soil which permits flow of water through it, that is basically called the permeability. It's a soil property. It's a compactness, it's a sand silt clay, it's a structure, it's a texture, it's arrangement. All these property makes this mass means soil mass, its characteristics in terms of permeability. So soil is highly pervious when water can flow through it, just like one example is gravel. You just take the gravel, put the water, not a single drop will move horizontally, it will go down. So it's a highly permeable. In another condition, maybe a soil which is not permeable or very low in permeability. So impervious soil, the permeability is very low. For an example, it's a clay. If it is pure clay, it will not allow much water. Few drops in a whole day, maybe something like that. Or say rocks are impermeable. But remember, we are talking about irrigation. If you are going to fluid dynamics, design of say dams and structures, even these have a little bit permeability. It takes years to pass, but it passes. So seepage is there. Another term is seepage. So we are talking about the irrigation, and this is the characteristic. Means we have applied water within a short period of time. It must reach to the desired depth, and that's why permeability, movement of water within a system or within a condition, it is required to understand. So what are the factors affecting permeability? Two conditions, soil as well as water. So in soil, it's a soil particle size, properties of pore fluid, means which type of water, means what is the characteristic water. If it is brackish, it is means fresh water. The density is perfectly whatever it is fresh water. So it has all effects. Void ratio of the soil, like you have seen, it's different. Void ratio VV upon V means volume of voids divided by total volume. So it depends on these characteristics of soil, shape of the material, just like texture, structure, lattice structure, or it is cubical, spheroid, whatever structure. So that makes the shape of the mass. So structure of the soil mass and degree of saturation. Permeability means it is permitting. If it is a kind of, say, clay soil or clay soil, its permeability will be more when it is saturated. When it is dry, it will first absorb. So permeability, the particular condition we are measuring, will be less. So these are the condition. Then goes to hydraulic conductivity. That is our basically target. Saturated flow condition means two-phase flow system. So hydraulic conductivity, just let me first introduce and then I will get into detail. So hydraulic conductivity, basically once we are simply telling hydraulic conductivity, it is saturated hydraulic conductivity. Saturated means soil is completely saturated and it is like addition one drop on the top will give you one drop at the bottom. It is connected flow. So saturated hydraulic conductivity is termed as hydraulic conductivity and presented by Ks, capital K and small s. That is S for saturation and K is hydraulic conductivity. It is measure of soil ability to transmit water when submitted to a hydraulic gradient. What is hydraulic gradient? It's a difference in hydraulic head. You have learned in your soil technology classes, I think. Did you get introduced to hydraulic conductivity in your second year soil technology classes? Students, please. Sometimes I feel that I am alone here. Yes or no? Somebody joked. Have you learned about hydraulic conductivity?
Sir, a little bit, I think. Yes, I remember the term.
Okay. Let me then complete this here. Okay. So it's a measure of soil ability to transmit water when submitted to a hydraulic gradient, difference in head. Difference in head condition. Head means pressure head. So in sometimes means at the last when I will ask, that's why I have introduced it here as well. It is proportionality constant K of Darcy's law. So that gives an idea what is hydraulic conductivity and what is Darcy law. So factors affecting hydraulic conductivity or saturated hydraulic conductivity is basically media property. Media is soil, so soil type, soil properties, sand, silt, clay content, etc., etc. So all these media property affect the hydraulic conductivity, as well as fluid characteristic, means flowing fluid, that is water. So if it is fresh water, it is saline water, its density, its temperature. So all these factors are affecting the hydraulic conductivity. Sometimes, or most of the time, or we can say in groundwater studies, this hydraulic conductivity is termed as called as coefficient of permeability. So you have learned, that's why I have started from permeability. It allows water to pass through it under certain condition, that is saturated. Once it is saturated, it is called coefficient of permeability in case of or in studies of groundwater. Now, here you have seen hydraulic gradient. What is hydraulic gradient? It's important to know first hydraulic head. I know that you have already learned in your soil technology, but let me refresh you. Hydraulic head is elevation with respect to standard datum. Datum means reference line or reference point, you can say, at which water stands in soil. If we put a piezometer, what is piezometer? It's open from the bottom, simply pipe, and if there is water, it enters into the water until it is equal amount of the pressure there at this particular point. Pressure means water pressure in soil. So soil water pressure it reaches. If it is saturated, it will go up to the saturation level and so on. So it is elevation with respect hydraulic head is an elevation with respect to standard datum, that is reference line, at which water stands in a riser pipe or manometer, that is called, connected to the point in equation or in question in the soil. So at this point, what is the hydraulic head is simply measure of head from this point, that is called pressure head, and difference of this point from the reference level, that is called the elevation head. So it is called basically the hydraulic head. Suppose for an example, can you answer if I put this datum or reference line, this is say groundwater table because it's a soil surface we have taken. Let me put this datum or reference point at the ground surface. What will be the pressure head in the means hydraulic head in that case? It will be simply from this ground surface to this level. So this depth will be the hydraulic head because by definition it is difference from the datum head or datum point to level of water at the point. It is called the hydraulic head. It includes elevation head, you can see it is elevation head and pressure head as well as velocity head. But here in soil saturated condition movement of water, velocity is very negligible and it's usually non-turbulent. So for non-turbulent flow of water in soil, the velocity head is negligible. V square by 2g, velocity is almost zero. So velocity head is negligible. So once we are finding out total head, that is called the hydraulic head, elevation head plus pressure head, that is quite sufficient for saturation or saturated condition movement of water in the soil or within the soil. That is basically the definition of hydraulic head. Now goes to Darcy law because it's important here. We discussed hydraulic conductivity and Darcy law. So what is Darcy law? Basically Darcy or Henry Darcy in 1856. Remember, infiltration equations were started developing in 1932 and US SCS has developed the last equation in 1957. 100 years back, 1856, Darcy investigated the condition of saturated flow of water through sand beds first and then gave a general relationship for movement of water inside soil at saturated condition, and that is called the Darcy law. This law states, you can see, this is the simple idea. What Darcy did, it prepared a sand bed or sand condition for his experiment, subjected one side a pressure head, that is H2, and outside, because it's a H means inflow condition, this side is inflow and this is outflow. This is simply flow is because of this high and low flow condition. In another equation, you can see it here in better way, here like this. If this is a soil or basically sand, I will show you Darcy's experimental setup as well later on. So if this sample or porous medium, that is soil, is subjected to two pressure means high pressure condition, that is inflow side, that is H in, the outflow of water will be in terms of its loss condition of head. So this law states that flow rate through this porous medium, that is discharge Q, under a subjected head condition, that is H in, it is measured from this datum. This line at the bottom, it is taken as datum. And head is measured at inflow and outflow through these open condition, means the pressure of water, it is showing here. So from datum to the point of water, that is subjected as input pressure of water to this soil sample, and at the outlet side it is measured and it is simply recorded to see what is the head at the outlet side where Q is the discharge. So this law simply states that flow rate through a porous medium is directly proportional to the head loss. What is head loss? It is head towards input condition and it is head at the output condition, outlet condition. So difference in this head, that is basically the head loss. Basically it was head like this and it has reduced now, so difference is head loss. So this law states that flow rate, that is Q, through a porous medium is directly proportional to the head loss and inversely proportional to the length of flow. So flow rate is the velocity per unit area. Let us take first. So velocity of flow per unit area, because this is area of a flow rate, means velocity per unit area, that is velocity, or flow rate per unit area, that is velocity, is simply proportional to the head loss h1 minus h2, or h2 if we have taken here, then h1 is here. So difference in head, and it is inversely proportional to the length of movement of water or path of flow, that is L here, that is L. So finally, once we are combining these two conditions, Darcy got velocity of flow of water in this porous medium per unit area is simply minus K, R is proportionality if we are taking, then delta S by L, and it is equal to minus K delta H H2 minus H1 by L. So simple idea is Darcy related the velocity of flow per unit area in this soil or any soil in saturated condition is simply because of head difference or gradient, basically it is called head difference, and the flow path length, and it is one equating condition, that is minus K, that is called the constant, Darcy's constant, and this Darcy constant is basically known as hydraulic conductivity or coefficient of permeability in case of saturated flow characteristics of soil. This term basically H2 minus H1 here by L, only this H2 minus H1 or delta H by L, the change in pressure head, basically what it is, the change in pressure head per unit length of flow or per unit flow length is known as hydraulic gradient. Delta H by L is known as hydraulic gradient, and that is usually denoted by small I. Then the Darcy's law can be written B, velocity of flow, is equal to simply Ki, and this negative sign you have seen here as well as here. It is basically indicating, or its indication, that the direction of velocity or flow is towards the decreasing head side from this to this. So suppose you are in vertical phase of soil, vertical space of soil, capillary rises from bottom to up. So it's not always that it will be negative there, it will be positive. Simple reason, flow is occurring from high to low side pressure condition, it is represented as a negative condition only. So this is the basic idea what Darcy has given. Flow of water in soil as medium under saturated condition is related with hydraulic gradient, that is delta H by L. Now this is the velocity or movement of water per unit area. So unit is simply centimeter per hour, millimeter per hour, millimeter per second, meter per day, or whatever. So it is simply L by T. The equation of flow per unit time through a given cross section area. Now let us take this section area means cross section area of this porous medium sample we have taken, that is A. And for a particular time, or here let us first find out for a unit time. So that is basically becoming discharge area into velocity or flow of water, that makes the total volume. So it's per unit time. Discharge cubic meter, now it is cubic meter per unit time, per second, per minute, per hour, whatever we are taking. It's a simple Ki, that is hydraulic conductivity into hydraulic gradient and the area. But once we are taking for a particular time, we can multiply T as well in both sides. So Q is now here the quantity of flow per unit time, and also usually in 12 or our understanding purpose, it is referred as flux of water per unit time, that is flux of water. It is called flux basically. Now, this was the original setup which was used by Darcy. 1956. The porous medium sand was filled. There were two means input side pressure condition and output side pressure condition. It was measured simply H2. Here it is written, it's basically expression, and in flow side it was H1. So difference in head is delta H, H1 minus H2. And they, from this type of setup, Darcy gave this relationship that velocity is proportional to the difference in head and inversely proportional to the length of flow. And the relationship finally becomes velocity is proportional to the hydraulic gradient, delta H by L. Now, once we know this Darcy law, now you know the Darcy law that B is equal to say Ki or Q is equal to Kia is the Darcy law, which was given by the Darcy in 1856 after experimenting a sand-filled container or porous medium. Sand was taken there. So there are few assumptions Darcy has assumed, or it was assumptions behind Darcy's law, that soil is completely saturated. It must be saturated. So this flow, V, velocity of flow or discharge from the flow per unit time, or flux of water flow outside from the soil, we are assuming it is coming from a saturated condition soil. So soil is saturated. That is the assumption of Darcy law. The flow through soil is laminar. Remember, what is the laminar condition? Means it's two-phase flow condition. Means there is no velocity head. Remember, we have learned previously that it's a no velocity head. It's only pressure head and gravitational head. No velocity head there. So flow is laminar. It's almost zero or negligible velocity. So the flow is continuous and steady, means fixed rate of entry. That is basically assumption behind the Darcy's law. Total cross section area of soil mass is considered total. It's no matter what is the size, but we can consider. However, it must be uniform system. There must not be any heterogeneity in the of same side, means it should be the same granular condition. That's why Darcy has taken a sand-filled container for this experiment. And the temperature at the time of testing, it was measured there 27 degrees Celsius. So these are the corrections. If we are changing temperature, it can be corrected for the right information. If we are deriving the output or taking into account the Darcy law. So Darcy law is applicable as long as the flow is laminar or non-turbulent, simply meaning velocity head is not generated there. And for the flow to be laminar, the Reynolds number must be, or that is defined as rho v d y mu, where rho is the density of fluid, v is the velocity of flow, P is the diameter of particles or particle medium diameter size of soil, and this mu is dynamic viscosity of the fluid. So once we are getting Reynolds number value less than 1 for saturated soil flow condition, it is termed as simply laminar flow condition. Otherwise, it is turbulent. In soil flow system or soil three-phase system saturated flow condition. For laminar, Reynolds number should be less than 1. You have not learned about the groundwater, but let me tell you, once it's a groundwater flow, this Reynolds number increases up to 20 sometimes. Reason being, there is a non-laminar flow condition exists as well. And once it's a pipe flow system, later on we will learn when next topic I will be picking, water conveyance and control in farms. So in pipe flow system, Reynolds number is considered as laminar condition when it is up to 2000 or less than 2000 in pipe flow because it's pressurized flow condition. And beyond 2000, it's non-laminar condition. We will discuss later on that. So this is these are the assumptions behind Darcy law. It simply states that velocity v is equal to ai. K is saturated hydraulic conductivity, or that is constant in Darcy law, which represents the soil property that is called saturated hydraulic conductivity. And I is hydraulic gradient, that is simply equal to delta H by L. And delta H is difference between input and output condition heads, and L is the length of the sample. So once we know the Darcy law, it has a kind of practical condition. You need not to think about the container, experiment and same, but you have learned in land and water resources engineering how to find out the water that is moving inside soil. One is entry, because we are learning irrigation. So irrigation as well as previously learned land and water resources engineering, you might be interesting to find out what is the amount of water that entered into the soil and how it is moving. So it is suppose the big area in a basin. We need to find out what is the amount of water that is moving in different depths of water, soil, that is different layers of soil. So we can use this Darcy's law to find out quantity, that is discharge Q, that is velocity of flow from the Darcy's law, and multiplying by the area which we are considering. You can take reference point either ground surface or groundwater table to find out the flow of water from these two places, from say upstream side of basin to downstream side of basin. We need to find out what is the hydraulic head there. It is now the matter of head, which forces water to move in a particular direction. So hydraulic gradient, suppose in the big area, you want to find out at 2 points having sufficient distance. It is simply the piezometric head or pressure head of water at that particular point A we are measuring, and at another point B we are measuring, and distance between these 2 points that gives hydraulic gradient. Then we can find out what is the flow of water condition from A to B or B to A, depends. And finally, we can find out what is the total amount of water that is moving per unit time or per day, per month, something like that, under these conditions. So this is basically the application of Darcy law, and later on 2 more applications I will show you here. So this is saturated hydraulic conductivity, what we want to learn. An important aspect is Darcy's law. So Darcy's law gives an idea about saturated hydraulic conductivity. Or proportionality constant in Darcy's law is saturated hydraulic conductivity or hydraulic conductivity. Any query about this?
No, sir.
Anybody? It's clear. Now the
Yes, sir.
question is how to find out hydraulic conductivity, because it has an important bearing. Suppose we have applied water in the field, it will enter into the soil, that is infiltration, and then it will move within the soil in two conditions. One is saturated and another is unsaturated. So unsaturated is percolation, that we are not discussing here, but it can be measured from the same infiltrometer ring condition. What about hydraulic conductivity? How to find out? Because hydraulic conductivity is important to find out how much amount of water Q discharge. Flux is per unit time, but suppose we have time. How much time it will take to reach this much amount of water to this particular depth of soil? So movement of wire means water in soil layers after saturation, that is our interest. So we have interest to measurement of hydraulic conductivity. If we know the hydraulic conductivity K, we can find out the velocity of flow, we can find out the discharge that has been taken place in the soil after its saturation. So this is our target, how to measure the hydraulic conductivity, measurement of hydraulic conductivity. So Darcy's law, that is the sole support for us. So Darcy's law is used for determining the hydraulic conductivity of soil samples or soils in the laboratory. If it is soil sample, it's in laboratory, or in situ, means in the field condition. If it is soil, we have interest. So it's a field condition. In situ means field condition. So Darcy law is used, and you know now the Darcy law, that is Q is equal to KIA. K is hydraulic conductivity, I is hydraulic gradient, and A is the cross section area of the sample or soil we have taken into account, and Q is equal to discharge per unit time. So in laboratory method, there are two ways. Either we have soil sample in prescribed condition, or we are going to the field directly to measure the hydraulic conductivity. So in laboratory method, determination of K, there are two methods basically: constant head permeameter and falling head permeameter. So two methods are there. In situ or in soil field conditions of measurement, the same Darcy's law is applied to measure and find out field saturated hydraulic conductivity, and it can be done by infiltrometer approximation. If you recall, infiltration characteristics or infiltration of soil becomes constant after a quite long period of time. What does that mean? Means whatever water enters into the soil, it is replaced or it is moving in the same amount of water from the lying soil below the surface. So means what? Water, whatever it is entered, it is moving through the soil as well. So moving through the soil, that is basically hydraulic conductivity. So if it is uniform distribution, or say simply material or soil is homogeneous, then whatever it is entered into the soil from the surface as infiltration will pass on from this soil layer. So in that way, infiltration information or measurement of infiltration characteristics, when it is stabilized, can be taken as approximate hydraulic conductivity or saturated field hydraulic conductivity. So that's why it is by infiltrometer approximation. So that infiltration rate which is stabilized is approximately saturated hydraulic conductivity of that soil. Another method or instrument we are using, that is double tube permeameter, to measure in situ or in the field condition determination of saturated hydraulic conductivity. Third method is air entry permeameter. So permeameter is air entry that is used to estimate back the saturated hydraulic conductivity. When it's agar hole method, we are putting a agar in the means agar hole in the soil, or we are putting or developing a hole in the soil. Then we are filling this to find out what is the rate of loss of water to make a constant condition of water. That is basically the idea of getting hydraulic conductivity. Then pumping test, there are conditions when water is very near to the soil surface, or sometimes it is almost at the topsoil surface. There are conditions. In that case, we are putting just a hole in the soil and starting pumping and finding out a rate of pumping at which the entry of water from all sides to this hole is constant. So that is basically approximation condition of hydraulic conductivity of that soil, where a constant rate of water is pumped out. So rate of pumping out is simply approximation or measure of hydraulic conductivity there. And it could be a reverse pumping as well. When soil is unsaturated, water table is far below, we are filling a hole that we have prepared in the soil to make a constant head. Whatever amount per unit time we are adding there in that condition, it is simply condition of saturated hydraulic conductivity after quite long period of time. So these are the methods. Reverse pumping method, let us remove the test. Pumping method, agar hole method, air entry permeameter method, double tube permeameter method, and by infiltrometer approximation method. So these are the methods of measuring in situ or in the field condition hydraulic conductivity. And in laboratory, we have two methods, constant head permeameter and falling head permeameter. Have you covered these two in the soil technology class? That I suppose to be. That's why I am asking. Students, have you learned constant head and falling head permeameter methods in your laboratory class, in your theories during soil technology subject?
No, sir.
No. Then I need to explain it. So you want to take a break or let us finish? Because I have taken just 15 minutes. Let us finish if we can. Okay? Yes
Yes,
or
sir.
no? Okay. So it's a constant. I am just explaining you laboratory method. Two laboratory method I am explaining you because explanation of this is means could not be possible here. So what I have scheduled in lab experiment, I will take just one laboratory method and one in situ method to let you understand how it really works or how these methods of determination of hydraulic conductivity works. So in theory, let me learn laboratory methods of determination. So suppose we have, this is a particular setup where this soil sample is subjected to a head of water that is inflow, means this is subjected, this level of head is subjected to supply water to this soil sample, and it is approaching this supply of water from the bottom. So this is a particular lab setup condition, and water after saturating this sample is coming up because of this pressure, and then it is flowing off from this system, from this opening. So opening has a particular measure. Measure means height condition. So we know that at what level of water it is coming out from the system. This soil sample is sealed both sides by porous plates. Porous plates means these plates are allowing water to move freely. There is no hindrance of water. So soil sample that is supported both sides from porous plate is fitted into this system to get inflow of water from the bottom, and once water is saturating this soil sample coming up here and flowing off the moment it is reaching to this level. So it's a constant pressure condition. That's why constant head method it is called. Pressure we can make constant. We are adding water in this pool, and the moment it is going beyond this level, it is flowing up. So at any condition, the head in this inflow side is not going to more than this level. And in outside of this sample, once soil is saturated, water coming up here, there is no chance of increasing head at this side. The moment it is touching this opening, it will go out. So head difference means if we have such kind of setup in laboratory, we have subjected this soil within this porous plates, water is filled to this inflow chamber or inflow reservoir. It has provision of airflow to maintain the head, and outside it is we are collecting the outflow in a certain time we are measuring. Then we can find out the hydraulic conductivity of this soil sample. Usually this sample is saturated. So observations, what are the observations here? Measured discharge for a known time. This is coming out flow or discharge from this sample. So that is amount of water Q volume in time, particular time. Suppose T time we have observed, and Q discharge or Q cubic meter of water we have collected. We know that this is a specific setup. So this has area of this soil sample, that is considered suppose A. Then measured head difference. This is inflow head, this is outflow. So this outflow is taking place because of this difference. You know it very well from fluid dynamics. So it's a head difference, that is H here we are representing, or usually we are taking H1 minus H2. So this is from standard reference you can take, suppose here at the bottom, this is H1, this is H2. So difference between H1 and H2 is delta H. So measured head difference between inflow and outflow is H. So this discharge is taking place from the soil because of this head difference. Then from the Darcilla is very clear to you. B is equal to Ki minus Ki means usually from high to low head it is moving. So usually we are taking minus Ki. So velocity of flow per unit area of this sample is simply Ki. K is hydraulic conductivity. Basically here we know it. R is proportionality constant in Darcilla, and I is hydraulic gradient, that is simply delta H by L. Delta H is head difference in between inflow and outflow condition. So we can take now the discharge because we have measured the discharge. So discharge is equal to area into velocity. We know the sample area, that is A, and B, that is velocity of flow we have measured. So now discharge we have measured, that is AB. So it is simply is equal to A K delta H by L, and it is in time T. This discharge in time T. So now to find out hydraulic conductivity of this soil, K is equal to simply we are taking QL, that is making balance, QL divided by A delta H and T. So A T H, H is basically delta H, that is head difference. Now if we have measured precisely the discharge in time T coming out through this sample, under this sample is subjected to a head H1, head of water, and water is coming out with reference at H2 head condition, then delta H is simply head difference. That is here it is represented by H. So hydraulic conductivity is discharge we have collected. We know the length of this soil sample, that is L. We know the area of this sample. We know the time for which we have collected this water, and we have measured the head difference, that is H. So we can find out what is the hydraulic conductivity of this soil. And this is the basically method we are using in laboratory, and it is called constant head method of estimating hydraulic conductivity in the laboratory condition. Do you have any query here? Is it clear?
It is clear, sir.
Okay. Now, second is falling head variable condition. Now it's almost same setup, but here we do not have a reservoir which is supplying water at a constant head condition. Means it has provision in constant head condition that any water heading to this reservoir is flowing out, overflow. Now here we do not have that kind of condition. We have simple condition of supplying water, collecting water that is coming out from the soil sample that is subjected to a head from inflow side or input side, and output condition here. So here using the Darcy law, same Darcy law is used everywhere, either it's a laboratory method or it's a field method. So in second laboratory method, that is falling head per millimeter, basically it is called. Discharge measured in time t in this outflow condition, T2 minus T1 two time, means starting time and ending time. Suppose we have started exactly at 10:00 or 10:00, 10 a.m. exactly, and after 5 minutes, so 10:05. So that is delta T is 5 minutes starting from 10 to 5 T1. T2 means 10:05 and T1 is 10:00. So simple idea is discharge measured in time T, that is delta T, that is QT, total discharge in say T times 5 minutes, 2 minutes, whatever it is, total discharge is simply Ka, that is hydraulic conductivity. A is the area of sample, T is already here inbuilt, so need not to multiply, that is not flux, that was not flux. It is simply in this supply side, we have a tube which is supplying water as input to this soil sample. So it is the starting time, tube was filled up to this level, and after delta T or say simply T2 condition, it is emptied up to this height. So it is difference in height of water in this supply tube from HT1 to HT2, that is delta H, or change in head in inflow tube. Outflow is for sure, it is HT, means that is basically the head from the beginning condition, that is HT1. And at the second condition means when inflow side it is reduced head condition, that is HT2. So here we can see that discharge that has been collected from this sample in time t is equal to Ka, K is hydraulic conductivity, difference between HT1 to HT2 here inflow side, right? Head difference delta H and divided by L. So head difference from HT1 to HT2, that is basically creating difference condition, or from here as well you can take HT1, here head difference was HT1 and now it is HT2 when it is reached. So difference between these two conditions, HT1 minus HT2, is creating this discharge what we have collected in time t, and that is related. However, if we are seeing this tube which is supplying water, which has a certain diameter, cross section area, that could be maybe small a, and in the same time that is delta T, that is giving a volume of water for this height which has dropped the water head in this tube, right? So here in this first condition or first equation what we have prepared, Qt is the rate of flow through the sample as a function of time t, and these two are ST1 and ST2 are the hydraulic heads as a function of time which is created or which has created the flow occurred through this saturated soil sample. The rate of flow, that is Qt, is simply equal to the rate of, means this rate if we are considering rate of this is simply equal to this rate of fall of water in this supply tube. Yes or no? Yes or no? Means the rate of flow Qt is equal to simply the rate of fall of head in this supply tube multiplied by the cross section area, because this is volume of water. Yes or no? Nobody is answering. I think it is
Yes, sir.
making difficult. So you are tired.
Yes, sir.
So
Without
let
break.
us stop this now here. I will complete this falling head meter in 2 minutes. Next time we are taking class. So if you have any query, because 2 minutes, let me give you to ask you any query if you have.
Sir, in this
Starting from infiltration. Yeah.
sir, in this constant head or falling head, some water is also in uh, on the top of soil sample
In
which is not collected in the beaker, no, sir.
here, here.
Ah, yes, sir. That water is not included in Q value.
No, 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 that is not. Means only what we are collecting. Means this is just for the graphical representation. Otherwise, you can say that it has any pressure on this. So it's a basically pressure on this soil sample at the bottom. But simply this flow is occurred because of the head difference. Otherwise, we can move this outlet exactly at this here, this level, as well. Means there is no pressure at the outflow side. That is as well possible. So this is a graphical representation. This water is not considered. Reason being, only water which is coming out from this sample per unit time, means whatever it is going inside the soil, coming this side, that is only pushing this flow. This is basically a push flow system. You know that if it is a, suppose a container, it is completely filled. There is no force of gravity which is creating here the flow. So if you add just one drop at the top, what will happen? You do not have any space to accommodate that one drop. So it will be coming out one drop from the bottom. This is the same system. Means it's adding here and it is going out exactly the same amount here. So this flow, which is means collected in this beaker, you can see, or any container, that is considered as Q. Is it clear?
Oh, okay, sir. Yes, sir.
Okay. Any other query? No query? Then I assume that you are very clear, and then remain portion of this method, falling head laboratory method, and other applications of hydraulic conductivity I will explain in next class tomorrow. Okay?
Yes, sir.
And only 42 students are there. Okay. Have a nice time. Hope for next class and see you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.